Hello, my name is Mohammed Bello Hamisu and I'm going to be talking about magnetic levitation. Magnetic levitation is the product of the repulsion generated as a result of two magnetic fields. It is a technology that is used presently in the world in high-speed trains with linear motors. The chassis levitates due to magnetic forces. In 1842, a scientist called Samuel Earnshaw proved a theorem from his name called Earnshaw's theorem, which says that it has been proven that levitation cannot be stable only by using permanent magnets. Magnetically levitated motors are kind of motors that rotate while levitating, also known as bearingless motors. This is a picture of a simple magnetic levitating pencil. As you can see, the pencil is levitating. Magnetic levitation by diamagnetism. Magnetic levitation by diamagnetism is what we have said broken Earnshaw's theorem. This allows graphite to levitate in a non-contact manner without controlling anything on the permanent magnet. A substance which has relative magnetic permeability less than 1 is called a diamagnetic substance. Relative permeability represents how easy it is to magnetize object. Graphite board does not stabilize with a single magnet. It will be stable when the magnetic flux is zero. Example of a diamagnetic are our body and also water, because if we enter a strong magnetic field, we shall levitate. There are different applications of magnetic levitation: the Yamanashi maglev, the Linimo maglev, and the Shanghai Transrapid. The Yamanashi maglev is a very high-speed railway. It is the world's fastest speed on train, exceeding 600 kilometers per hour. It runs up to 150 kilometers per hour on tires, which is marvelous. It actually recharges its tires and levitates like an airplane. The principle of the Yamanashi maglev. Magnetic levitation needs coil to levitate magnetically and also needs coils to move forward. These coils are called levitation guidance coils or figure 8 coils due to their peculiar shape. They all line up on both sides all along the railway. So, when a vehicle with superconductor electromagnetic approaches, a current is induced in the figure 8 coils. A repulsive force comes from the lower side and an attractive force comes from the upper side of the coils. Then the vehicle levitates. It is necessary to cool the superconducting magnet to minus 200 degrees Celsius. This is a picture of the Yamanashi maglev. Next, we have the Linimo maglev. The Linimo maglev, which is derived from linear motor. Linimo runs at lower speed than Yamanashi. It does not require superconductor electromagnets, so there is no need for cooling system. The train is levitated even when stopped, in which construction is way cheaper. It also doesn't require coils on both sides of railway. In this case, there's something like an arm, which is right below the under the track. There are electromagnets around the palm of the hand. When current flows, the linimo floats. The principle: there is a contact point called pantograph. Through this contact, electrical energy is transferred from the rail to the train. Pantograph takes electricity from the railway to levitate and move forward. Basically, it is a magnetic levitation system by feedback control, and there's an advantage that superconducting magnets are not necessary. This feedback is trains are affected by various external forces such as slope and wind. There must be a distance between the vehicle and the rail. They control distance by attaching a gap sensor. Since an output is being measured and the sensor is being used, this is called a feedback. Next, we have the Shanghai Transrapid. The maglev in Shanghai, China, runs up to 431 kilometers per hour. It is originally a German technology. It is similar to Linamo maglev because it levitates with electromagnets. The levitating system also lifts the vehicle from underneath. The maglev in Shanghai is the only high-speed maglev that runs commercially. This is a picture of the Shanghai Transrapid. We have many other applications of maglev. For example, in the stationary blood pump, it provides life support to patients with severe heart diseases that are in big trouble. A professor at a university in Kyoto discovered that patients can live longer if they use blood pumps with a magnetic levitation because they avoid the formation of blood clots and thrombosis, increasing the longevity of the patient. It really provides life support while patients wait for a new heart. We have we also have high vacuum turbomolecular pump. It is a pump that makes vacuum and also used in water pump for processes with high purity, like semiconductor and liquid crystal manufacturing. The benefit of maglev for a pump is that impurities can never come in. In vacuum pumps, grease is applied as a lubricant and the grease evaporates, and it is difficult to make it a complete vacuum. But with magnetic levitation, you can avoid this, achieving high speeds like 50,000 RPM. The 21st century will be the century of maglev technology. Next, I'm going to explain the mechanism of an electric train. Electric trains have a similar mechanism because of the use of motor and inverter features. The principle of DC was discovered in 1830, but motors were used as toys at that time. In 1870, powerful motors were really developed. There are two types of motors. We have the DC motor, which is also known as direct current, and we have AC motor, which is also known as alternating current. The rotational speed of a DC motor can be easily controlled by changing the input DC voltage. The speed of an AC motor depends on the voltage frequency. It requires inverters and more complicated control technique. DC motors need a component called brush, which make contact between rotating and static parts. These brushes wear due to friction, so regular maintenance is needed, while on the other hand, brush is not needed in an AC motor. The world's first electric railway was in 1879 in Berlin, Germany, in which there was no automatic voltage control for this motor. Steam engine and generator adjusted the speed of the vehicle. The speed of DC motors can be controlled by varying the input voltage, but unfortunately, the technology to adjust the voltage was not available at that time. The first electric car was also in Berlin 1881. The difference between the first electric car and nowadays electric train is that voltage is applied on the railway, which means humans and animals can be electrically shocked. DC motor principle plays its role since then and also used in the Japanese bullet train around 1967, which became the world's fastest high-speed transport, the Shinkansen. Shinkansen was driven by a DC motor and later replaced by AC induction about 30 years after that. There's a really use of an inverter because of an inverter is a unit that can convert DC to AC current. So when combined with a rectifier, which converts AC to DC, we can convert AC to DC and then DC back to AC. In 1992, about 30 years after the first Shinkansen, the inverter technique was applied to it for the first time. After applying it to Shinkansen, almost all electric trains in Japan became electric trains. Electrical engineering advanced significantly due to inverters. This is a simple inverter circuit. So when we turn on the switches, we have four switches in total with a voltage source and a resistance. When we turn on first switch and the fourth switch, and we turn off the second switch and the third switch, a closed circuit marked with a red line is completed. Downward voltage is applied to the resistance R. On the other circuit, on the third circuit, when we turn on the switches, the second switch and the third switch, while we turn off the first and fourth switch, the voltage direction applied to the resistance is reversed, as you can see. Considering the direction of the voltage change, it acts like alternating current. Thank you. This will be the end of my presentation.